Alright, AP Statistics students, we are looking at Chapter 7 and we are finishing it up with Lesson 7.3, which deals with sample means. So we are continuing to look at sampling distributions, but now we're going to focus on the sampling distribution of sample means. Before we dive into that, let's go over this decision-making tree, which deals with inference. You're going to hear that again in this video, this idea of inference. And as we go further in the semester, we're going to start hitting that right-hand side more in this decision-making tree. But Chapter 7 really is that first part of the branch, the first branch of, are you dealing with a population parameter that's a mean or a population parameter that's a proportion? So when you're reading it, you have to figure out, am I dealing with a mean or am I dealing with a proportion? And then as we go into Chapters 8, 9, 10, we're going to start going further along that decision tree and looking at the different tests that we're going to do. But right now, we're looking at, okay, am I dealing with a mean, a mu? Am I dealing with a proportion parameter, p? So when we're looking at that, keep in mind, sample proportions are often used with categorical variables. But when you're looking at numerical calculations like the mean, the median, the standard deviation, you're looking at quantitative variables, and sample means are among those common statistics that you look at with quantitative variables. So right now on this screen you have two histograms. You have one that deals with a population, and you have one that deals with a sampling distribution of sample means. So if we have, in this case, the population, and that's the left one, this is our population distribution. And we are looking at this, we want to analyze our shape, our center, and our spread. It always comes back to what we first learned in Chapter 1. What's the shape, what's the center, what's the spread, and that tells us what calculations we can do. So right here, and I would encourage you to write down that this left histogram is a population distribution. And if I want to figure out what is the shape, I'm going to be analyzing and go, okay, well that shape, it looks slightly right skewed. I mean, that's a right skewed distribution, which is pulling the mean of that over to the right-hand side. So it's a right skewed shape. And the center, if I were to look at it, it's actually labeled for me, and that is approximately 75. So they had mu there, and it's approximately 75 thousands of dollars for household earnings. That's the center, mu, because it's population. The spread, now we can't calculate a numerical value, but we can describe it. And since it's right skewed, it is stretched out along that right side. So I'm going to say there is a large variability here. It is spread out pretty far. And if I were to even calculate the range, even is a very large number. We don't like using range, remember. So when we go through, I can tell it's a large variability. Now when we look at the right-hand side, that is a sampling distribution of X bar. And that's where I'll go back to the original prompt where it says, hey, you had sample size of 100. So what that means is, we took a population, we took a sample of 100, we grabbed it, we calculated the mean of that sample. And then we took another sample of 100, and we calculated the mean of that sample. And we kept plotting these on the x-axis. And that's where we get that shape from. And we're going to dive into that as we go here. And so what's the shape of this one? And this is interesting. The sampling distribution of x bars, if we look at it, it looks approximately symmetrical. It's mountain-shaped. Even. Now if I look at the center, and if I were to trace down the center of it, it is close to the same one. It is approximately 75, but notice the label there. Mu of x bar is approximately 75. I didn't say mu, because it's not the mean of the population. It is the mean of the sample means. It's the mean of the sampling distribution of x bar, so it's mu of x bar is approximately 75. And if I go into spread, again, can't do a calculation. But I can describe what I see. And this one's tighter. I mean, this one has a smaller variability than the other one. And so that's interesting to notice about our sampling distribution and the relationships of them is what happens in this case. All right, so by the way, another reason I could tell before we go on to the next slide that these are not the same types of distributions. One's a population and one's a sampling distribution of X bars is look at the variables on the X-axis. This looks at the household earnings in thousands of dollars for that population distribution. But notice this variable here, the mean household earnings for sample size 100. So any value, if I grab that value, that is the mean of a sample of 100. If I grab a value from here, that is the household earnings for that person. Here is the mean of the household earnings of 100 people. So it's this idea that these graphs are not the same thing. So if we have a sampling distribution of X bar, it always goes back to shape, center, spread. And so when you have many simple random samples from a population, you grab many of them. So don't just ignore the writing. If I look at this, I'm grabbing many as simple random samples from a population. I'm grabbing, and I'm calculating X bar. I'm calculating the sample mean of each one of those. Here's what happens. If you have an X bar is the mean of a simple random sample of size n drawn from a large population with a mean of mu and a standard deviation of sigma, here's what happens. And so really, let's just talk about shape, center, spread. But I want to kind of focus on a couple things. Notice it right here. A simple random sample. You have to keep in mind that we need to make sure things are done randomly. That was chapter 4. When we looked at inference in that chapter, we started to say that word inference, and it has to be done randomly of size n. And so that's interesting as well. I wonder what we're going to dive into with that size n from a large population. That's capital N where we define it. So here's what happens. If you have the sampling distribution, this was what we looked at in the previous slide, the population, which is right here, that's the population mean, is going to be equal to the mean of the sampling distribution. Let me say that the other way. The mean of the sampling distribution is equal to the population mean. And that's what we saw right up here with the centers, the blue part. Mu was 75, and mu of X bar was 75. So when you have a sampling distribution that follows the proper procedures, and we're going to go into that, you will have mu of X bar equals mu. The sampling distribution mean, the mean of the sample distribution is going to be equal to the population mean. Now, if you have the 10% condition, if 10 times your sample size is smaller than your population, then we can deal with, ignoring independence without replacement. We can look at this formula. The standard deviation of the sampling distribution is the population standard deviation divided by the square root of n. So this is the standard deviation of the sample means is going to be equal to the population standard deviation divided by the square root of n. And when you divide by a number, because remember, n is going to be a number, it's your sample size. When you divide by a number, it makes the number smaller and smaller and smaller and smaller. So notice, we said we have a small variability for that sampling distribution of X bars. We had a larger variability for the sampling, for the spread for the population. So notice, on that right histogram, it got tighter and tighter and tighter. And that's kind of where you can see why that occurs with this formula. Is you're taking your population standard deviation, you divide it by the square root of n. So some of the things to keep in mind, I said don't ignore that top sentence when you're going through these things, because that's really where a lot of meat of the concepts and the properties and the characteristics come into play. I mean, notice right here, this, you need to know what that label means. You hear me saying it all the time. This is the mean of the sampling distribution of X bar. I mean, notation is huge. That's what that's saying. What is mu? Mu is the population mean. Well, oh, by the way, what about this? As long as the 10% condition is satisfied. Isn't that interesting? If it is drawn from a large population, was said in the beginning, and we talked about why random is important when it comes to inference. So a lot of these things, keep in mind over here. Don't just throw them away. It's interpret what's being said in these boxes. But notice I've highlighted there on the bottom. These facts about the mean and the standard deviation of X bar are true no matter what the shape of the distribution has. So no matter what shape the distribution is, these are always true. And we're going to put that on hold, put it on the back burner, and we're going to come back to it later on in this video. So now we moved on to the next slide. This discusses what is a sampling distribution of X bar. And I know, you looked at this with p hat. But remember, you have a population where the mean is mu, and that's that group of people over there. And what you're doing is you are taking a simple random sample, again you see random there, of size n. And notice all of those simple random samples are going to be the same size right now. And you're calculating x bar for each one of those. So, population, grab a simple random sample of size n, calculate x bar. Do it again, calculate x bar. Do it again, calculate x bar, ... and continue doing that. And what you're doing is you are really taking those x bars and you are plotting them. And so take a look at this. I'm going to take it, I'm going to plot that x bar, I'm going to put them on that line, and I'm going to keep doing it. I'm going to repeat it over and over and over again until it starts stacking up. And when it starts stacking up, notice it becomes approximately symmetrical, it becomes mound-shaped, and it's going to become, in case, approximately normal. And so this is our main idea. This is the picture. And the reason why I have all these x bars here is because each value there is a sample mean. That distribution is a distribution of the sample means. It is a sampling distribution of x bar. So each value there is a sample mean from a simple random sample of size n. And so we can see that. And notice the labeling here. What do you see here? It's labeled. We can see our shape. That looks approximately normal based off of that. We can see our center. So what does that mean? That means, mu of x bar is equal to mu. We can see our spread. Our standard deviation of x bar is equal to the population standard deviation divided by the square root of n. So I wonder, now that I know shape, center, spread, can I make a statement? Can I say shape, the center, and the spread? So that's pretty interesting. We can actually do that now. So main idea behind this picture, and we're going to go to the next slide on this, is for you to see each value is an x bar and a sampling distribution of sample means. All right, so now with the next slide, we are looking at the sampling distribution of x bar from a normal population. So there's going to be two cases analyzed with sampling distribution of sample means, and that is case 1. And case 1 is the population is normal. And we'll look at case 2 later on in the video. So if you have a population and it is a normal population, you have the shape is normal, your center is mu, your standard deviation is sigma. And what we're going to keep in mind is take a look at what we're dealing with is if we have a sampling distribution, which means I am looking at many samples of size n taken from a normal population, and we're calculating the mean of those, and we create a distribution from there. So that's really what that picture was in the previous slide, is I'm taking many samples of the same size, calculating the mean, throwing it on a distribution. And that's what this case is going from if the population is normal. So again, population is normal. What happens is if the population is normal, then the sampling distribution of sample means is going to be normal as well. And that is true no matter what the sample size is. But what that no matter means is how small the sample size is. And I want to stress that it is how small the sample size is. So let's look at the box. So we have a sample distribution of a sample mean from a normal population. So suppose that a population is normally distributed with a mean of mu and a standard deviation of sigma. And that's where you see that n parentheses mu comma sigma. The sampling distribution of x bar, so notice the phrasing you have to write, is a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. And that's what we talked about on the previous slide as well, as long as the 10% condition is met. And that's why I want to say it's true no matter how small the sample is. That 10% condition, beware, remember, is it does matter if your sample is too big in that case. But I want to stress something here. I want to talk about what's really going on. Is realize everything always comes back to 4 things for us. Was our data collected randomly? And so notice it goes and says, hey, you have a simple random sample. And so we want to make sure that we collected the data properly. Because if we collect it randomly, we can do inference. So we always want to make sure we see that word random in these prompts when we're going through it, or we know it's being collected randomly, or if we set up the collection of data, we can make sure we're doing it randomly through samples. Then what we want to look at is next is, hey, what's the center? And in this case, we know from a sample distribution of x bars that your mu of x bar is equal to your mu. And then we go, okay, well, what's next? Well, what's the spread? Well, for the spread, we know that the standard deviation of x bar is equal to the population standard deviation divided by the square root of n if the 10% condition is met. And well, once we know that, then we can finally say, well, hey, what's the shape going to be? And well, in this case, the shape is being collected from a population that is already normal. So therefore, the sampling distribution of x bar will be normal as well. So we're really still focusing on the same stuff we started with before, which is random, shape, center, spread. These all start to culminate together. So now we're going to look at an example of this, and we're going to kind of talk about some differences with these next few slides. All right, so here we are looking at the example. We're looking at the young women's heights. And remember, we've dealt with these examples for quite some time. And we're going through this. It says the height of young women follow a normal distribution. So right there, it is telling me that the population distribution is normal. So when I'm reading, I have to pay attention to a lot of this. The mean mu is 64.5 inches. The standard deviation is 2.5 inches. So find the probability that A, and I want you to, it's underlined for you, but circle highlighted, is it says a randomly selected woman is taller than 66.5 inches. And the reason why I'm saying to circle that, highlight that is this a sampling distribution? And the answer is no. Because you have a normal distribution for the population, and it's saying find the probability that you take one person from that population and that young woman is taller than 66.5 inches. So this is really chapter 2. And so we start to realize we have to be careful with our reading when we're looking at cumulative questions. Is it saying find the probability that a randomly selected, that one randomly selected young woman is taller than 66.5 inches? And what you're looking at here is, think about it in general, is you're taking a population and you have one person being selected from that population. And you're going to compare how that person relates to the rest. So you're going to go, how does this person compare? That's chapter 2. You have a population, you grab one person, how do they compare to the population? So we're not looking at a sampling distribution yet. So this is an intentional example here. We want you to be careful with the reading. So let's start it though. We have, find the probability that a randomly selected young woman is taller than 66.5 inches. You have to define the variable. I'm going to say it. If you don't define it, you don't get to use it. That's a little flashback to what you went through before with the videos with this. So let x equal the height of a randomly selected young woman. One randomly selected young woman. Well, if I look at this, I am told the population, it has a shape that is normal. So I have a normal population. The mean is 64.5 inches, and the standard deviation is 2.5 inches. Again, we're looking at chapter 2. So I'm going to find my z-score. So I'm going to take my statistic minus my parameter. I'm going to take what I observe minus what is expected, and I'm going to divide by my 2.5. So I have 66.5 minus 64.5. I'm divided by 2.5, and I get 0.80. So I have that z-score. And by the way, notice I have my picture there. And what I'm going to do is I'm going to have the graph magically appear. Boom. So I have the shape, the center, the spread in notation. I have it in the picture. I'm set, and I'm going to go through everything else. So I have here that the probability that x is greater than 66.5 is going to be equal to the probability that your z-score is greater than 0.80. Now, the reason why I like to label down there the 64.5, the 67, and so on is I can see, my z-score matches the location. And you really should also write down what that lower bound represents there. It represents 66.5. Now, I like to use normal CDF because it's a lot of fun. And when you go through it, you can do that, or you can do 1 minus your table A. Remember, table A gives you area to the left. So if you go to table A, you're going to get 0.7881, but you have to do 1 minus table A to get it. And so therefore that gives us our probability is about 0.2119. So the probability of choosing one young woman at random, whose height exceeds 66.5 inches is about 0.21. So notice the idea here. This is telling you slow down with your reading. Just because you're in sampling distribution chapter doesn't mean everything deals with sampling distributions. It's a cumulative program. It's a cumulative course. You have to be careful and make sure you understand it. Now, when I look at the next part, the height of young women follows a normal distribution. So again, this is telling me the population distribution is normal, which means if I collect a sampling distribution, it too will be normal. It's the same information, but this time the prompt has changed. It says find the probability that the mean height of simple random samples of 10 young women exceeds 66.5 inches. So we are looking at simple random samples. So I'm grabbing, hey, here's 10 women, what's their heights? Here's 10 young women, what's their heights? Here's 10 young women, what's their heights? And I'm taking the averages of those. So I am collecting a sampling distribution. So notice the difference in phrasing here compared to the previous prompt. And we have this set up on the side, and so I know it's not a lot of room for you, but I want to make sure you understand we're checking random, we're checking center, we're checking spread, and we're checking shape. We need to make sure that it was done randomly, because that allows us to do inference, and that's where we're going. So make sure when you're reading this, it does say a simple random sample of size 10 was selected. Remember for center, the mean of the sampling distributions, of sample means, the mean of the sample means, mu of x bar is equal to mu. So therefore, when I'm told mu is 64.5 for the population, when I do a sampling distribution of x bars, it is going to be the same for the mean of the x bars. And it's a lot of saying sample means and distribution, sample distribution, sampling distribution of sample means. It can be very, very intimidating with the phrasing, but we learned this. And I'm going to come back up to our picture. And when we go through, we could see that our sampling distribution, the mean of that sampling distribution was the same as the population mean. I could see it as well with this. The mean of the sampling distribution was equal to the mean of the population. And so all that phrasing is really saying that. All right, what's the spread? Well, we'll hold on a second. Can't do the spread yet. Is my 10% condition met? So 10 times my sample size is 10 times 10, which is 100. Good. So is 100 less than or equal to my population? Well, I should define my population. It is safe to assume there's more than 100 young women. So because of that, I can do my spread. And I go, okay, all right, 2.5 is the population standard deviation, square root of 10, and I'm going to get about 0.79. So that is smaller than 2.5. Remember, when you do the spread of a sampling distribution, it got tighter. So that standard deviation should be smaller. All right, so the shape. Well, now that we have that, we can say the shape. Since the population is normal, the sampling distribution of x bar will also be normal. It's going to have the same center. However, its spread, its standard deviation is going to be smaller. And it's that 0.79 we calculated. And now we still go back to what we did before. We're going to find z-scores. And so I'm going to take, 66.5, that's what I'm trying to figure out, exceeds 66.5, so you can see that right here. Well, what am I going to do next? Well, I'm going to subtract my mean. It's the same mean, mu of x bar equals mu. However, divided by the standard deviation is now 0.79. And in this case, I get 2.53. That's interesting. And so now, I want to know the probability that x bar is greater than 66.5. I want to know the probability that z is greater than 2.53. Notice I have, and it's on the bottom left of the slide, I'll circle it right here, I address shape, center, spread down there. I also address it in my picture. I have the shape, I have the center, I have the spread, and now I'm going to graph it. But look at that. Can you see it? It's way over here. And I'm still going to do this. Here's 66.5. So notice, that's way off to the side in this case. And that's interesting that it's not the exact same picture as what we dealt with before. So here's what I have. I can do 1 minus, or I can do the normal CDF. Remember, in this case, it would be normal CDF your lower bound, 66.5, your upper bound, it's almost the same exact thing as this. But even if I take this, let me just duplicate it and drag it down, what's different about it? Well, the difference is going to be the spread. That's going to be the different part. And I think it was, 0.79 if we take a look at it, but everything else I could keep the same. So that's interesting that the spread lowered. All right, so it is a very, very, very small, unlikely chance, less than 1%, that we are going to choose a simple random sample of 10 young women whose average height exceeds 66.5 inches. But I want you to pay attention to the conclusion. We don't just say what the probability is. It's not that the probability is less than 1%. That distribution, this right here, is really a collection of X bar, X bar, X bar, X bar, X bar, X bar, of the same sample size. So notice that we're saying, hey, it is very unlikely that if you choose a simple random sample of size 10, that the average height will exceed 66.5 inches. We are trying to make sure we understand the context. It's not that, hey, there's 1%, less than 1% chance that the height exceeds 66.5 inches. No. It's a less than 1% chance that if you collect simple random samples of size 10 repeatedly, the average height is going to exceed 66.5 inches. And that's what we're going to go into as we go further into this lesson. So what have we learned so far? I'm going to just go to this screen right here. And this is where this video is going to end. And the next video will begin after this slide. Because the next video looks at case 2. And I'll talk about that in a minute. But here's what we learned. We have that population standard deviation. And we have that sampling distribution standard deviation. And we saw how the population had a large variability. And you see that spread there. And when you have this sampling distribution of X bar, it got tighter. The standard deviation got smaller. So the standard deviation of X bar was tighter. It had less variability. And so what you really see here, and I remember I said how that shaded area was a lot smaller on that one when we had the sampling distribution. And so imagine that green, and that green is the sampling distribution of X bar, and that purple is the population distribution. So can you see that shaded region? Notice that shaded region, it covers a lot more of the population, but because the sampling distribution of X bar got tighter, it had less variability, notice that shaded region is a lot smaller. So it's going to have, in this case, a different z-score than the other ones are because it has a less area in that curve than the other one does. So this is kind of talking about what we notice about our pictures and the shapes. So bottom line is everything comes back down to random, center, spread, shape. Case 1, and that's what this video covers up to. Case 1 is if your population is normal, the sampling distribution of X bar will also be normal based off the characteristics we talked about in this video. Case 2, and that's what the next video looks at, is what happens if the population distribution is not